Swayam Prabha. Digital India. Educated India.
Hi, welcome back. So, I'm going to try and do a concise discussion on 3D boundary layers, 3D turbulent boundary layers. Okay. To do that, the first thing is I start with 3D boundary layers, 3D laminar boundary layers, and then introduce the turbulence into it. Okay. So let's go ahead and start to do that. Okay. Now, so I have this curved surface, right, which is arbitrarily curved surface, and it looks something like this. Okay, right. That and this let's just say the shaded area is your boundary layer. Okay, so this is actually so this is an arbitrarily curved surface. Yes. Okay, so this is actually S. What is x1 and x2? I'm going to write that right away. Okay, so I'm going to draw an axis system. Let's just say that. Okay, okay. Why don't this is an orthogonal axis system. Okay, so this is x1 right. What is small u? Small u is basically velocity within the boundary layer. Capital U1 is the free stream velocity component in this direction, which we are calling as x1. Okay, this one is x2, u2, right, and this one is actually x3 and u3. Okay, now I haven't written a capital U3 there, meaning velocity component of the free stream. Well, the free stream we're taking as that it has two components only, which is in the x1 direction and x2 direction, and x3 is the direction which is always perpendicular to the plane formed by x1 and x2, right? Right, then this, right, is the boundary layer edge, right, and this is the delta, which now depends on x1 and x2, which now depends on x1 and x2. Okay, so this is orthogonal curvilinear coordinate system. Okay, such that x3 is everywhere normal to S, to the surface basically. Okay, velocity components in the boundary layer, which is 3D in this case, right, are U1, U2 and U3, right. Then we have only 2 components of the free stream velocity, okay, which is then again x3 is normal to the wall, right. Yeah, so this is more or less the definition of the geometry that we're looking at now, right. So we're looking at the 3D boundary layer. Okay, so now x3 is normal to the wall, right, and the boundary layer is assumed to be thin. Yeah, so x3 is normal to the curved surface S, right. Boundary layer is thin, right. So based on this, we basically say right. So boundary layer is thin in the x3 direction, right. So basically we are saying that velocity, the velocity component in the direction which is perpendicular to the x1 and to the other 2 coordinates is actually much smaller than the velocity components in those 2 coordinates, and therefore so that's essentially it's like saying in the laminar boundary layer, when we ignore the velocity components in a 2D system, right, what we've learned earlier. So in the vertical, in the direction perpendicular to the flow, that's the direction in which the boundary layer develops, and we take the velocity v in that direction, we kind of neglect that, right, we neglect that. So we're trying to do the same thing here. So basically we're saying that the boundary layer thickness depends primarily on x1 and x2, right. So span wise and laterally, right. So if I were to sort of explain that a little more, for example, you could have if I'm looking at a flat plate, this is the plate that you've looked at earlier, right, and the boundary layer forms on this, right. So let's just say this is C and this is X, right. So boundary layer falls on this. Now what happens is that you are actually considering even the span, so that you also have another dimension which is y, right. So which is y direction. So in this, if you compare it with what we have here, so this is the x1, this is the x2, and this is the x3 direction. I think that's simple to see, right. So in that case, now what we are basically saying is that the thickness of the boundary layer, right, in this direction, in the z direction, thickness of the boundary layer in the z direction compared to here in the y and in the x direction is much small, right. So what the kind of profiles that we've seen earlier were how, something like this. So this was like at, right. So this one, so we used to say this is u, right, and we would take the velocity there to be 0. So what we are saying now is that exactly even here. So if I were to look at this location, right, this location, it has a certain x. So say this is say let's just say XA and YA. Yeah, so probably YA is 0 here. We can, this is one location, right? So I can move to another location. I can move to another location, right? Let's just say I move to this location, right? This is a plate now, so I'm going to look at it this way, right? And then I draw a velocity profile boundary layer like that, right? So in that case, if say I move here, right? So here, how will the boundary layer behave? So same location. This is just this is also XA, except that YA value is not 0, right? So we've actually made a travel along this, which is your delta Y. We've moved there, right? So in this case, how will the delta, right? So delta is this is your thickness, right? So how does that delta behave if I make changes in the delta Y direction? If I make a delta Y change right? So delta will change. The point is delta will change. And again, delta, so delta therefore depends on Y, right? So we wrote down that it depends on x2, right? And again, if we, so if here, so then we could again, look at another location, which could probably be, say here, where we move along, say here, okay? So then here, what sort of velocity profile should I look at? Then similarly here, what should I profile look at? Okay, because now you are moving from between x along x direction without changing the y, right? So what will that? So that will also change. That will change. I think that we know from before. So this will also change. So we wrote down that delta is a function of x1 and x2. Right, x1 and x2. So now the point is the boundary layer is thin. The boundary layer is thin. This thickness is thin, such that and x3 is normal to the surface, and hence we are basically saying, since the boundary layer is thin, so there the u3, which is the u3 component of velocity, which is in the z direction or x3 direction, is much smaller than the other two. Okay, so this is something that this is part of the assumptions that we make for this solution. Okay, so now let us go ahead and develop the relationships. Okay, now first, of course, what I'm starting to do is the boundary, the 3D boundary layer, right, and then I'll introduce the turbulence. Okay, so general orthogonal system, right? Now an element of arc length ds, right, is related to the coordinate system, actually x1, x2, x3 through scale factors, which are h1, h2 and h3. In what way? In this way. Okay, is equal to okay. In this case, however, now this is from basic math. Okay, so you can look this up and you can study it in as much detail as you need to, right? So here I'm not going to go into the details of this. This is from math, okay? So these are you should be able to get the details of this on any standard mathematics book, okay? Through scale factors, so in this case, however, right, x3 is everywhere normal to the surface. Right, and therefore H3 is equal to 1, okay, everywhere. Now, if the scale factors, now these, I'm going to speak briefly about the scale factors, okay. Now, if the scale factors are not known, right, so you can develop your own, surface, and then, put it in this form. However, if the H1, H2, and H3 are not known, they can be found relating it. They can be found relating it to the any Cartesian coordinate system. Well, using the definition actually. Okay, let's see how we do that. Okay, so H is 1, right? Now, if the scale factors are not known, they can be found by relating right to any convenient Cartesian system. So, H1 square, right, is essentially del x del x1, right, del y del x1 plus del c del x1. Right. So, this again I can write this also as del x1 del x square, right, plus del x1 del y square plus del x1 del z square. And let me also write down H2 is the same, right. So, del x del x2 del y del x2 right. So, yeah, so that's that, right, and right here of course H3 is equal to 1, okay, and then of course H3 is equal to 1, okay, right. So, now finally, so basically we essentially have this arbitrarily curved surface S. We have defined curvilinear coordinate system x1, x2 and x3. We have two free stream velocity components, and these are velocities within the boundary layer. Okay. Now, with that, so we had to this H1, how do I calculate H1 now, right? The moment I do this, so the H1 it can be related to the x, y, z, basically the coordinate system in which one is solving this, trying to solve this problem. Then they can be connected to the local coordinate system, and that's what we've done here. Okay. Now, so finally, using these coordinate systems, the incompressible continuity equation exact will look like this. Okay. So, in these coordinate system, right, the incompressible continuity equation, okay, right. So, that looks like, so in these coordinate system, right, there is the incompressible continuity equation, exact incompressible continuity equation looks like this. So, 1 by H1 H2 right, plus del x2 right, plus del okay. So, this is the continuity equation. Okay. Now, boundary layer is thin, boundary layer is thin, right. Because the boundary layer is thin, the normal pressure gradient right, can be neglected. Okay. So, that is my continuity equation. Now, let us write up the momentum equations. Okay. So, now we write up the okay. So, these are the momentum equations. Then okay, plus u1 u2 h1 h2 del h1 del x2 right, minus u2 square h1 h2 right, and this is equal to okay, and then you have the viscous term. Okay. So, this is the momentum equation in the x1 direction, right. So, similarly in the y direction, similarly in the x2 direction rather, okay, u1 u2 okay, minus okay. Now, that is equal to okay. So, this is your equation in the x2 direction, right, and the third equation is actually, so in the third equation of course, so del p right, this is in the x3 directions, right. So, this is the continuity and these are the momentum equations, right? So we have the continuity, and these are the momentum equations. So x1, x2 and x3. Okay. Now here let me write down a few things. Okay. The operator, so d dt, okay, 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 yeah, so these are the three equations, and we have this operator here. Okay. Now finally, the boundary layer thermal energy, okay, the boundary layer, so the 3D boundary layer thermal energy equation can be written in terms of the total enthalpy. Okay. So the 3D boundary layer thermal energy equation can be written in terms of total enthalpy. Okay. So enthalpy here okay, and then okay, okay. What PR, of course, PR is the, if you've not already noticed, is the Prandtl number. Okay. So this is the Prandtl number, right? And alpha is equal to K by rho Cp, right? Now where, now for steady flow, okay, then, okay. Steady flow, Prandtl number is equal to 1, right? Prandtl number is equal to 1. So if you see here the total enthalpy then, okay, the total enthalpy then is constant everywhere if the wall is insulated. Make sense? So if you look at this equation here, so Prandtl number is equal to 1. For steady flow, Prandtl number is equal to 1, which means this term will completely vanish, right? So what we are left out with here should tell us that the total enthalpy is H is constant, right, everywhere, and if the boundary wall is insulated. Okay. That is, Crocos relation is not affected by this by three dimensionality. Okay. All right, that's something to sort of point out here. Okay. Then the pressure gradients, right. Now the thing is, okay, so these are my equations. Let's just focus on that page. So these are the three equations that we are talking about here. Okay. Now the pressure gradients must be matched to the free stream velocity, which has two components, W1 and W2. Okay, so let's write that down. So now the pressure gradients right, must be matched to the free stream velocity. So if you have done a class on, introductory class on boundary layer theory, then you would have calculated how the pressure gradient is related to the free stream, right, just outside the boundary layer. You would have done that, and you take this location which is just near the edge of the boundary layer, and then you implement that. Okay, so if you have done some introductory course on boundary layer theory, if you haven't, then you have to do it now. Okay, all right. So so the pressure gradient must be matched to the free stream velocity, right, which has essentially two components. So this is the velocity. So it has two components. Okay, and U2 is also. So you can see here that the free stream velocity is basically dependent on the two coordinate systems, x1, x2, two coordinate axis, x1 and x2, and of course it is time dependent. Okay, so now the proper matching is given. So these things basically have to match. The pressure gradients and the velocity components need to be matched, and this is done by Euler's equations of inviscid flow, right. So the proper matching is given by Euler's equations Okay, so let me write that down. So we have minus 1 by rho h1 okay. Okay. Okay, then okay, and okay, so the matching in the x direction is given in this fashion. So I'm going to basically repeat myself when this is in the x2 direction. So let's just write that down. Okay, this okay plus yeah, so this one should be U2, okay, then U2 by H2 is del U2 del X2, yeah, X2 plus U1 U2 H1 H2 right. So, this is the correlation between the pressure gradients and the velocity components in the two Cartesian coordinate systems. So, we did all that. So, then what we finally need is boundary conditions including a porous wall. Okay. So, then right at x3 0, so finally, okay, so let me, well, this is obviously intuitive, but anyway, let me introduce that here. So then this is for boundary conditions, okay, including a small porous wall. Okay. Okay. Okay, and T is equal to wall temperature. Wall temperature, and I am calling the velocity in the x3 direction to be equal to Vy, okay, which varies as per x, y and time. Okay, and T is the wall temperature. T is the wall temperature, right. Now, at x3, at x3 is to infinity, okay. So, x3 tends to infinity. What does this mean? So, this means nothing. This means that once we are away from the surface, there is no boundary layer. The boundary layer fades. So, then the it slowly resembles the the free stream around it. Okay, that's all it means if you look at it. Okay. So, this will holds at the walls also. Resultant wall shear direction may not be in the direction of the free stream velocity, probably is not. Okay. So, let me at least write that. Okay. So, resultant wall shear direction may not be in the direction of the free stream. Free stream, right, free stream velocity okay. So, we got that in place. Well, that's all really, that's all the 3D. So, what we started out doing. So, this is all about the 3D boundary layer. Okay. So, we are talking about okay. So, 3D boundary layer. Okay. Then, so what we now need to do about turbulent boundary layers is, yeah. So, now what the next job is cut out for us. So, we need to now develop the boundary layer equations in a turbulent regime. So, I do not think I will start that today, but let me just sort of talk about in generally, okay, about the turbulent boundary layers. Okay. So, we are now going to really talk about turbulent boundary layers, begin to talk about it in 3D. So, essentially we are looking at the 3D turbulent boundary layer equations. Okay. So look at high aspect ratio bodies. Okay, so high aspect ratio. What are the high aspect ratio bodies? Which is swept wings. Okay, where both span-wise and stream-wise gradients are small and the ordinary boundary layer approximations apply. So, for example, something like a swept wing, right? So, where we said that we've just said that streamline gradients are small, right? Streamline gradients are small, and the ordinary boundary conditions, whatever we have for a laminar boundary layer, they all apply here. Right. So, if you keep taking a section along the span, you will not need to make any further additions or subtraction, because the ordinary boundary layer equations, boundary layer assumptions, approximations will be valid, will be applied. Okay. Okay, these are high aspect ratio bodies, right, and the other is low aspect ratio bodies. Right. Now, low aspect ratio bodies, like, okay, when I said swept wings, okay, I'll draw those, a few. Okay. So, for example, corners, okay, wing tips, okay, non-circular ducts. Non-circular ducts, right. Now, span-wise gradients are comparable to normal gradients. So, let's just say, I'm going to draw a, so let me draw this, okay. So, say a swept wing. So, you can have okay. Okay, so let's just say okay. So, let's just say this is this. Okay. So, this is these are my 3 coordinate system. Okay. So, or I might draw this, let me draw that in a little better manner. Okay. Let me draw this a little better. It will be easier to see. Okay. So, let's draw that first. Okay. So, let's do this. Yeah, that's better. Okay. And then you have a coordinate system. So, let's just say this is your x, right, and then of course you have a in this, like in the plane of the board, and which is what I was actually trying to draw. So, okay, maybe I could draw that also. For example, I could actually draw it like this, a swept wing. Okay, let me take another page. So, I could actually draw it like that. Okay. So, then this is your x, right, and then yeah, that's better. So this is your x. Oh shoot. Okay, that's your y, and then this is your c. Right. So swept wings is something like this. Okay. So here both span wise and stream wise gradients are small, and the ordinary boundary layer approximations apply. So if you have a system like this, right, if you have a swept wings, swept wings could be many other ways also. You can have a path swept wing also. Okay. So basically what we are saying is that when you move along this direction, along the x or along the y, right, the variation in the boundary layer is very small compared to its variation in the direction which is away from the plane of the board, which is perpendicular to it, right. So essentially the same picture here. So the gradients, right, in this direction and in this direction. So if I look at this particular section or this particular section, right, in the y direction, the gradients are small. It will change, but it is very small compared to the change in the only one direction z. So therefore, this is essentially high aspect ratio bodies. These are swept wings, right, and so we have to classify this, and immediately what we have is low aspect ratio bodies. Now for these, however, this is not applicable here. If you move along x and y, there will be a non-infinitesimal change in the gradients, right. So the gradient is not going to be cannot be disregarded. So so now we have divided these two sort of classes of problems, and then now we will see that how the boundary layer, how we will formulate and set up the problem for 3D turbulent boundary layers. Okay, so I'll stop now, and we will continue this in the next class. Okay, thank you.